Hello, and welcome back. To start, I would like to apologize for the delay. I meant to have this out a couple of weeks back, however, through a series of life events, I was delayed until now. For today, I will be going over OpenDDL and OpenGEx, as well as the parsing paradigm, and I will also be giving a scope or a look into the scope of what is currently being built. First and foremost, what are OpenDDL and OpenGEx? DDL is the Open Data Description Language. DDL itself is a generic exchange format which is used to create high-level formats. OpenGEX is a file format derived from DDL which aims to encapsulate the exchange of game engine assets across various build tools. Ultimately, game assets are not left in their GEX states but converted into an intermediate format which will capture the relevant data according to the game framework. This intermediate format is then converted one additional time into a binary database, which is written directly to memory on load. The binary database acts as the persistence layer across the game framework and the build tools. The binary database is invoked through a runtime database, which is given authority over a proxy of the binary database. Should it be desirable, the runtime database may add or remove entities from this copy, and at any point, the master binary file may be used to reconstruct a clean proxy file. The ultimate motivation for moving in this direction next after the terrain is twofold, and I believe I've made comments to both in prior videos. The first reason is the animation system. Until this point, I was undecided on a file format I wanted to use to capture scene data, and in my research, GEX seems to be the most solid choice, although this choice does come with its own challenges, such as a lack of readily available tools, but we can always build our own. The second reason is related to the multi-threaded code I showed prior. The code itself works fine in isolation, but under high contention and a real runtime environment, the solution was not scalable. A runtime database provides the logical synchronization point between simulation and rendering, and for the sake of transparency, this is the step I am currently working on. Now for the remainder of this video, I will focus back in on DDL and GEX and show a parsing paradigm that I'm using to go through these files. So to start, we're going to look at OpenDDL first. And the paper itself begins by describing DDL as a generic text-based language that is designed to store arbitrary data in a concise, human-readable format. Ultimately, this is achieved by collecting strongly typed data assets in the file into tree structures. These tree structures contain a fully built version of that logical type. The language also provides a mechanism for making references across trees. As I previously mentioned, DDL is not very high level, meaning that it tries to not impose too many arbitrary rules on the writer, but rather allows those rules to be derived into other file formats, one being GEX, which we'll look at later. And at the heart of the DDL file is the structure, and the structure can be thought of as like a building block. The structure itself may contain other structures, be contained in another structure, or both. Each structure has an identifier, the static typing of the structure. Following this is an optional name as well as an optional property list. The data of the structure itself is enclosed in curly braces. This is very similar to the C-style syntax. There are two types of structures, the first being a primitive structure. These are the structures natively defined by OpenDDL. Like many languages, they include integral primitives, as well as booleans, strings, types, references, and base64 data. The other type of structure is the derived type. These can be representative of any user-defined type, so think of like your C++ classes, or even C structs. The rest of the paper really just goes on to talk about handling the primitives and the rules for identification, and I'm going to skip over most of this as it becomes more self-evident when seen in the parsing code. One thing I do want to mention is the section on comments and whitespaces. They're handled similarly to comments and whitespaces in C, meaning that if there's a quote, then these should cease being parsed and be treated as part of the actual quote. In the actual implementation I'm going to show, this is not accounted for just due to how the test file supplied by GEX is set up. It works, In a future revision, I'll show the code change to handle strings appropriately. And this is actually a good time to mention that the DDL and GEX parsers will be made public, but there'll also be a living project, so to speak. So as the project requirements grow and as the necessity for new features or modifications to the parsers be added, it'll be readily available for anyone to go and see should they be interested. But I just want to say that now so that there's no confusion as why it is a very not even halfway uh, completed implementation. And next, I would like to talk about GEX because for me it became a much easier problem to understand the parser and make an implementation I was happy with once I looked at an actual implementation of DDL and its derivative format itself. So GEX, of course, follows the same rules as DDL, meaning that any DDL compliant parser will be able to parse GEX data or GEX files. So then what exactly is the purpose of GEX? Well, it attempts to model the practical representation of common game engine structures. You can see that here. For example, things that are common to almost every engine are animations, bone information, camera settings, geometry, skinning data. The list goes on. GEX tries to provide that common middle ground that allows assets to be moved from one part of the pipeline easily into another. I won't be going over all the actual structures in the GEX spec paper, as they just describe what the members are and how the structures are to be used. But in the implementation, I will be going through and showing the process of parsing the example file and how that data is being exchanged. One thing I do want to mention is that GEX works with a system of objects and nodes. These nodes contain references to the objects that they are built up of, and the objects themselves can be thought of as actual game data, and nodes as invocations of the data or multiple data. So now I will be going over the parsing paradigm used for DDL. I'm saying paradigm here because, as previously mentioned, the full implementation is not complete. As game assets grow in complexity, their needs will be retroactively added into the parser and other various parts of the build tool. However, having a concrete and simple to use pattern allows these changes to be made with ease and without the worry of breaking other parts of the parser. The implementation itself is a cross between the builder pattern and the factory pattern, though factory here is called a generator as it reads a little more clearly. The builder pattern I found to be particularly useful because we have no guarantee of the order in which the data is laid out in the file versus the reader program. So, for example, in the reader we may have an integer followed by a string, but in the code we may have a string followed by an integer. We also cannot guarantee that all the data the reader program may use is present. Using this, we can partially build objects and use defaults for the remaining field. So for example, think of, again, we have a structure that has an integer and a string, but in the file we only supply the string. So we would use a default value for the integer. The factory pattern was found to be useful as generation of structures is a recursive procedure. There are two possibilities that are used to terminate recursion. The first is the inclusion of primitive data, as presence means that there are no more substructures to go. So you can think of that, let's say you have in the code something like this, and then in the file you may have something like this. This I32 would signify an integer, and you would just put some value there, 42, why not? And then when you parse this, it would pick up this is a primitive, there are no more substructures that can be found, so this is the end. The other possibility is an empty structure in which the structure is returned with only default values in its members, or it just has no members in general. So that would be, again, something like this, where in the file we may just have an S. So we know that in the code, we are trying to create this structure, but we have nothing to represent it. Or the other possibility is in the code, this structure itself contains nothing. By using these two patterns, the following parsing paradigm may be created. First, filter the file to remove all comments, new lines, and white spaces. Second, parse out top-level file structures into a list of to-be-generated structures. For every top-level structure in the list, begin a recursive build chain and descend in a depth, then breadth-like fashion throughout the object's construction. And in this context, a top-level structure is the parent structure. This paradigm does require some setup work, which may be accomplished with some initializers and pre-computed tables. The first piece of setup is referenced in the third step. In order to determine which build chain should begin, an initializer is called to create the DDL and derivative format type generators. The initializer maps strings representing the static type of instances of generators, or factors, that create a new factory type and invokes its build function. So that can be seen here. The generate type function will get called, it'll create the type of T, and then begin T's own build function, and the build functions of T are found in the derived structure and the structures themselves. So, for example, the name structure inherits from builder, and therefore it will now get a build function that can be used in the generation process. The second piece of setup work is found within the build functions themselves. Each build function will recurse until either an empty structure is encountered or a primitive type. In order for the builder to know which member it is currently building, another mapping of the types is used. This mapping stores the same strings as the previous map, but instead of factories, these strings now map to a unique ID. When a parser encounters a new type, it is referenced against the ID and that build function is invoked. And that can be seen here. So the substructure is going to find the structure type through this function, which just parses out the identifier, and then it looks into this map, which finds the identifier in the file and tells you what type this structure is. These mappings will be talked about very shortly and be made a lot more clear. So the first thing to look at are the initializers. The generators are pretty self-explanatory as it just creates a mapping to the name of the top-level structure and a new instance of a generator for that type. So in this case, in the code, we call what GEX describes as a metric, as a GEX metric, geometry node, GEX geometry node, so on and so forth. And a top-level structure, again, is one in which no other structures may contain it as a substructure. These can be considered a safe launching point into the build process. The second initializer is the static typing. This scheme was chosen to reduce the number of initializers called and potentially missing an application-specific definition. By allowing the call to the initialize extended types to be inside the GEX call, this allows other users of the reader program to simply call the GEX initializer and get all application-specific types included as well. The second thing to look at here are the types themselves. So GEX animation, for example. They are pre-computed into lookup tables separated by logical namespaces. By following the pattern used, this allows user-defined types to be safely added without colliding. And what this means is, so for example, DDL, the basic types, here are your primitives. They are written into the DDL buffer types namespace and then given unique IDs. And if you wanted to add one in between here, for example, it's very simple, say you missed one, or say we add 128-bit floats. You would simply take the ID of the old one and then pipe the ID of the new one into the one that it replaced. And then now all these IDs will be updated going down the chain, as well as Let me get rid of that so I don't leave that in there. As well as any IDs that are created further down the chain. So, for example, the GEX buffer types, they begin after the extended types finish. And now there are no extended types here, but if a user wanted to create their own types following this style, they could just add their own, use the next buffer ID from the DDL, and then when GEX goes in, it'll start at whatever the ending ID for the extended types are, and that will, again, it'll allow for types to be added without causing collisions, which can be such a nightmare. One thing I would like to mention is that even though in the actual extended types there is nothing mapped, here we are initializing a few user-defined types. Um, this is okay because of how primitives are handled in DDL float, in this case is a primitive. The subarray expression inside the type, this right here, will be parsed away and the resulting float will be created. So that's why we still need to be able to track, is this a float 2, is this a float 3, 4, or 12? But ultimately, all of these different types of floats boil down to just a DDL float. So as previously stated, the structure is the heart of the DDL specification. Structures themselves are being modeled here as an identifier and a name. Both of these are just type defs for a string. Properties, or the property list for the structures, are excluded as they are actually specific to structure implementations and not structures themselves. Structures contain a vector of substructures which hold the building components of the structure. And finally, they also have a void star pointer called type heap, which is used to actually hold the object in memory. The type heap will point back to the object position in the main structure created by the generator. Currently, the system does leak as there is no cleanup for DDL files. This is not a problem, however, as the allocations performed during the build process in the future will all be done on a scratchpad allocator. So when the data has been transformed into the binary formats, the right pointer may simply be unwound and the scratchpad is reset. Since we are strongly typing all parse types, when the structures are to be used, it will be in a typed sense, so the application will know to convert that specific type heap into a GEX material or a GEX mesh, for example. This will become a little more clear in the next video where I talk about the intermediate format and changing from the DDL into the binary database. Alrighty, so now we can begin the parsing of the test GEX file on pages 8 and 9 of the GEX specification. So the first thing we're going to do is just look at the actual printout of the file, and we can see that stuff like the spacing, the new lines, and stuff like comments, these can all be filtered out really. Go ahead and zoom in so you can actually see it. And when we filter them out, we get a block of text that looks like this. The key observation to make here is that there is this kind of recursive pattern going on where you'll begin some string of characters. This is an identifier. You'll begin some scope count that you can treat an opening brace as the beginning of a scope and the closing brace as the end of a scope, similar to C++ and C. So here our scope count is 1, now it's 2. Now it's 1 again because we closed this one, and now it's back to 0 because we closed this one. So when our scope depth reaches 0, we know that we have encountered the entire structure itself. And this is actually how the top level structures are parsed out. We just clip the entire string up in using the scope counting, all the way through until the very end. And I will show that in a moment when we get to the actual parsing of the DDL file. This was just a little printout. But what's going to happen next is we're going to initialize those GEX types, which just goes through, calls the initialize extended, and we just add all of these things into the map. And these are all of the GEX specific types that we can encounter in the reader. And then we do the same with generators, create our generators. These are the generators for the top level structure. We create our file object, and we go ahead and start to parse the file object. So what this is going to do is actually do that parsing again that you already saw, and then filter the file. I'm not going to go through this code because, like I said, I believe comments and new lines and white spaces are not actually proper. So I'm just going to gloss over those, but the code will be public. So if you want to go check it out, you may. Then after we have that parsed string, this green block of text here, once we have that, we go ahead and pop into this partition DDL file function, which looks like this. So what this function is going to do is store in this result vector here all of the top level structures that have been clipped. So it'll store like this metric, it'll store this to here, it'll take the geometry nodes and go to here, geometry object, go to here at the material, and then take the material and go to here. And the way it does that, let's go ahead and step into it, is by that scope counting. So what it's going to do is it's going to say that we're going to start with no scope, and while the next opening scope, or the next opening beginning scope brace, is encountered before the next ending brace or closing scope, then we know that we are going down some depth level, and we are going to move into the file by that offset. And then we simply do a check here to make sure that we didn't hit 0 again, because if we hit 0 again, we're not in scope anymore. We can exit the loop, and the loop will exit with the accumulated offset, which now it should hit the else case, which it does because we only had 2 scopes on this one, and this is the third pass. So now we're going to find the next ones of these again, and once more we're going to close the scope. Scope depth is going to be 0. We have no more scope. That just computes. Then this exits, and we return the substring from the beginning of that filtered file through the filter offset. And then now we have returned the metric with the key, the distance, the float, and all that. So now, in order to make sure we don't just keep parsing out the same part of the structure, when this for loop increments, it's going to splice off essentially through that offset. So now, when we come back in here, if we check, load the memory, if we check our locals, we should see that it is still a metric, but now the file is beginning with a different metric. And we follow this pattern all the way through. Oop, don't want to stop debugging. Oh, geez. There we go. Too many hotkeys. We continue this pattern all the way through until we get all of our top level structures, which at the end here, we go back and check our locals. we have a list of 6 strings, and these strings contain all the information for our to be built or to be generated um, structures. So now that we have all of our top level structures, we are going to begin with each structure and get its identifier. From the identifier, we're going to find the appropriate generator, and then from that generator, we're going to call the generate type function. Generate type is going to create the new type in the type heap for this result that we are returning. This is the allocation I was talking about that is going to be moved to a scratchpad allocator. From here, we're going to call the build function on type T, which T has to be from a registered builder. From here, if we continue, we see that the first build function we encounter is that for GEX metric. The first thing we're going to do is parse the structure header. What this will do is it'll go through and find the payload identifier, the name identifier, as well as the property identifier. What this does is it sets up the result structure. We can see that when it's returned. And the result is going to store the potential name as well as the identifier that represents what this tree structure is, so that when we go to use the type heap, we know that what we are turning into. After we parse the header, we're going to partition the structure properties. And what this will do is it'll simply go through, and while there is a property, let's see if I can find one, it's going to capture the key and the value in pairs. And then it looks for these commas, which signify that there is another property in the list. Once it reaches the end, it knows to terminate, and then it returns you in a vector of strings the property and key pairs. For the metric case, it's a little simple because we know that we're only dealing with keys, but it also makes it very easy to demonstrate. The property list is actually a structure I think I forgot to talk about, or a mapping I forgot to talk about, where each structure has its own mapping of its own properties. This is very similar to the type buffers, but these are localized to the namespace of the structure themselves. So in this case, we know that we are dealing with a key because that is the only metric option possible, or metric property option possible. Then we set the actual metric's key to the value of that property. Once we go through each of the properties, similar to how we partitioned out each of the top level structures, we're going to go through and partition each of the substructures that are contained, in this case, in the metric. From there, we're going to look up the identifier type and return that mapped buffer type to get the case identifier. In this case, we're dealing with a float, so we know that the metric needs to create a new float, and the metric in this case is a little different than the rest, and I'll show it. But to handle its data, it actually uses a variant. Everything else is normal, but metrics are the only one that have variable data types. However, the process is the same for the rest. Now that the metric is storing the float, we go ahead and in the result, we're going to store a new substructure that contains the float. And on our newly created float, we're going to call its build structure, or its build function. This build function is going to return another result, or sorry, another DDL structure, and this DDL structure is going to be stored as a substructure of our current structure, or result structure. So let's go ahead and step into the build function for the float now, and this is actually going to be taking a look at the DDL primitives themselves. So the DDL primitives, as I previously stated, are a termination point for recursion. As you can see, there are no further calls to build. There are only 2 branches here, depending on if there is the presence of a subarray expression. Similar to other build functions, we're still going to parse out a header, but there are going to be no property lists. Now, we look for the inclusion of a subbuffer array. In our case, there isn't So we know that we are only going to be creating a float with room for one float. This is why the derived types were able to just say that a float 2, 3, 4, or 12 were all types of DDL floats. Because what the primitive is representing is a type of buffer that stores this data. It could be one of them, it could be a million of them. We don't really care, we just care what the strong typing of this region of memory is. But again, in our case, we know we're only dealing with one, so we're just going to create room for one. And this is a second allocation, which will again need to be done on a scratchpad. From there, we're going to turn what we know is a string representation of our float into the actual float in our data's buffer, or in our primitive's buffer, which in this case is the type heap for the primitive. After this, we go ahead and store the type heap and the result. So the primitive itself has its own buffer as the type heap that stores the data. But the primitive still needs to be linked back to the calling, the structure, the metric, which is why here we go ahead and say that the result we're returning, its type heap has, or it points back to this. And this is what you'll see in every build function at the end, as well as this that provides the mapping back to parent structures, as well as creating the reference map for other trees. And we can actually step into that function now, and we just simply see that if there is no name, we supply a new one, or we just take the one that's already there and insert our structure into the reference map. And after that, we simply return the result. We place it into our results substructures, and we are done with this particular metric. And again, we go ahead and store in the current result. So now we're in the metric, we are saying that the metric's type heap is this. And the reason why we're saying this is because, again, these are the member objects on which the build functions are being called. So in memory, if we actually look at where these objects are, the caller is this. So if we store this as the type heap, when we go back and call these during, or when we reference this data during the binary process or transferring the binary data, then we know that we are going right back to the memory locations which we built. And we just simply map the structure name again. And then after we're done building, we come here and then we store the type heap that we built to the result we're returning. And then now we have in our file object one complete, actually push it, one complete tree structure with its substructure. So I went ahead and skipped over the rest of the metrics as they really just follow that same process. So now we are going to pick up with the geometry nodes. And in this case, we have variable amounts of data that can be stored. And whenever that happens, we essentially create a vector, and this is really more of an array, but we just store some amount of data and hope that we don't need more than that. And in this case, it's I think 64. So we just store a bunch of memory for our build, and again, hope that we don't need more. 64 should be plenty if you really think about the types of data that we're transferring here. And so after that, we go through and we're going to parse our header, and we're going to get our property list. And now for each of the properties, I don't think there is actually any, but they would be describing, does this node have visibility, does it cast shadows, and does it contribute to motion blur? These are all just default properties that are in GEX. You can add more or not use them. They're just simply there for completion's sake. After this, we're going to go through and get all of our substructures, and then we're going to start switching on our type. And so the first thing we come across is not actually a geometry node specific type, but a node specific type, which is just the name. And so in this case, nodes are a little different. The build for the result doesn't actually store anything else because we're simply just piping this back to the previous in place. Show it to you. So here they're emplacing these when they build them. Here we essentially build it inside this and then store the result. And from the node, we just pipe back the result. We don't actually store the result ourselves. Or rather, we don't store the build, because the build is the result that we want to return. And here the name is just the resource name, so to speak. And we return the information, store the structure, and we simply just keep recursing through. And this is why I chose the paradigm that I did, because really, as you can see, once you have the build functions hooked up, they just begin to call one another. They just go through, and to poorly quote Todd Howard, it just works. Store the type heap, map the structure name, and then continue on. Now we go to the next one. We see that this is the object ref. So again, we're going to reserve the containers, parse the header. There are no properties. Go through, get each of the substructures. Because there can be multiple references, this is why, but currently we're only dealing with one. So that again is another change in the code that's going to happen. But we simply continue on, create the reference, and then references are actually handled at the end. And I believe I will be showing that in the next video. When the file is done and the database builder is brought in, that's when references are linked and hooked together. But we just continue to descend through, mapping as we go, storing the result as we go, and we descend further and further until we run out of substructures. And this, yeah, the transform. And this should be the last one. And so the transform, same thing. You go through, partition, and then the transform is going to be creating a primitive, but this primitive is actually going to contain a subarray expression. So in this case, we're going to go ahead and build the subbuffer, and how this is going to work is it's going to first create that partitioning again, and this is going to be our partitioning of all these subbuffer elements. So this is just the grouping of data. So let's say we had something like this. So that's telling us we have groups of 4. But again, we may have it stored like this. So we'll need to create 1, 2, 3, 4, 5 groups of 4 elements. So we'll need to store room for 20 elements, or 20 primitive types total. And that's essentially, and that's essentially what this code does. We go through, we create our list of strings, and then based on this list, we know how many subbuffers there are. So we go ahead and prepare the subbuffer, and this just simply allocates memory for all of the subbuffers, and or the number of subbuffers and the number of elements per subbuffer. And then what this also does is returns how many elements per buffer are there. Or actually, I believe, yeah, that's what that was. And then after that, we go through and extract the subbuffer by simply, for every subbuffer position, for every subbuffer chunk, we're going to turn it into the type that we are working with. And we're just using float here because even if we do turn it into an int, we're going to take a performance penalty on the conversion. But this is offline code anyways, so it's not the biggest thing in the world, and it'll align correctly. But we go through and simply just continue through our buffer until we have all of our data, at which point we will end here, and then we'll pop out, and just like with only one, we'll again store the type heap, make the mapping, and then return the result. And in here, actually, you can see the partition structure has, oh, no, that's what we just worked with. Sorry, here in the result, the substructure there we go, sorry about that. The substructure itself now has the float 12, and if we actually looked at this type heap, we can't do it now, but there is a printout at the end. It will go through and it will show that it in fact took all of this data and properly parsed it out. And now in the interest of saving some time, I'm going to just skip to the printout function here. And what this is going to do is it will print out the top level structure and then recurse through each of the substructures, with each of the substructures treating itself as a new top level structure and continuing down in the same pattern. And what we'll see is that the previously parsed information is all there. So we have our metric, which contains one substructure, that float, which contains 0 substructures. We have another metric, which contains 1, 0, 1, and 0. Our geometry node has 4 substructures, 1, 2, 3, 4, each of them containing one substructure, 1, 1, 1, 1, and each of their substructures containing nothing. We see the same thing here with the geometry object, where the geometry object has one substructure, the mesh. The one substructure, the mesh, has 4 substructures, the 3 vertex arrays, and an index array. These all contain one primitive, which contain 0 substructures. Actually, hope you can see that. And then finishing off the material. The material has 2 substructures, the name and the color, which with each of these again having 1, which are primitives, and they simply terminate. Now the next thing I'm going to show is that this actually works with, again, any DDL compliant or GEX compliant file. So here is one in which there are 5 nodes, 3 geometry objects, and then 3 materials. And if we switch the settings to read from this, or the test 2, what we will see is vastly more structures. However, it's exactly what we saw last time. We have the 4, the 1, the 0, 4, the 1, the 0, all the way down. Materials are the same. Geometry nodes are the same. The next thing I will show is an actual printout of the contents of the geometry node transform to show that the data is in fact actually represented in memory. So now I'm going to show the printout. However, before I do that, there was something that I saw when I was going through the code, and there's actually a departure from GEX here. Due to how the intermediate format is expecting transforms, we're always expecting 16 floats. So in the transform parse, actually after it's built, I go ahead and format that transform here, and it just simply takes whatever type it was. If it's a 3x4, 3x3, a 2x3, or 2x2, it determines how GEX was looking for that memory and then formats it in a 16x16 matrix. The GEX specification goes into detail about how the different representations of sizes look. I believe it's documented somewhere in the code, but not here. Well, I couldn't find it in the code, but here it is on the GEX specification. It tells you for 16 what the values are, for 12 what they are. It's on page 86 if you want to go in. But all of those transforms essentially just are put into a 16 by 16 matrix after the format. And there is one more bug. If you actually look at the printout, the transforms, their types are never updated to be 16, float 16s. Logically, they are. So it all works out under the hood, but the actual TTY is incorrect. So I actually had to rewrite the printout function because apparently I had it in row major order instead of column major order. However, with the printout, we can see that the data is formatted correctly to the 16 or the 4x4 matrix from this 4x3. The 4x3 in this case, according to the GX standard, is saying that the way this memory is read is that we have A, B, C, D, E, F, G, H, I, and J, K, and L. So basically, these just describe your axes, and then this describes your translation, which is exactly what is highlighted here. Now with that, that is the end of the video with the DDL and GEX parser. Thank you for your time, and to show you a little sneak peek of what is to come, in the next video, this is dealing with the binary database and the intermediate format. As you can see, the database the database was built from this intermediate format of MDBs, and then we also read out of the file and then loaded all of this data back in from our binary database. And this will all be covered in the next video. Thank you, and have a good rest of your day or night, morning, whenever you're watching this.